right, welcome back. So in the last video, I was sort of showing you, the ins and outs of a one sample t-test, right? Just sort of flying through it. But let's actually do one by hand. You can kind of see my process, and so you can get an idea of what's actually going on at a bit of a slower pace, right? Because we've got the time. Okay, so here it is, right? And this is very similar to what you might see on a test. Okay, so here it is. Here's a question. A local farmer has collected data concerning their alfalfa yield. So we've got that data down here. In the past, their mean yield of alfalfa was 1.5 tons. Okay, so a bunch of this stuff. However, the farmer notices that the yield on their test plots was more variable than last season. Okay. And they asked you to conduct your magic, right, your mathematical magic, to determine if the mean of their yield is changing in either direction, right? So no directionality as far as specific over or under the sort of this value, but they just want to know, hey, are my crops actually going to be different in some way this year? Or am I just losing my mind, which is totally plausible. Okay, and then regardless of the outcome from your hypothesis test, so whether or not we can conclude that our sample is going to be any different than 1.5 tons, construct a 95% confidence interval for the mean yield for the whole farm, right? So the population. We want to figure out, what, based on the sample that we have, can we kind of estimate the population mean, right, for the rest of the farm. Okay. Cool. So let's just get into it. Our research question, it's whether or not our sample, or do we have enough evidence to say that based on our sample, is the population going to be different than 0.15 or 1.5 tons, right? That's the research question. You can write that however you want. I'm not even going to write it, but what I am going to write is our null and alternative hypotheses, right? Because this is where a lot of the magic happens, okay? So our null hypothesis is that the actual population mean equals the known null, right? The known sort of last year's yield, right? 1.5 tons. And then the alternative, what we want to support, what we're testing, is whether the population mean, the actual population mean, is not mu naught, right? Is not 1.5. And we can actually write that over here, right? Cool. Okay, so that's the shorthand of it. But this is going to help us. This is going to help us with that T tool here in a little bit. Okay, what else do we need? Oh, you know what? Let's write out. We know our alpha. Well, before that, our confidence level is 0.95. We know that because it's said right up here, the confidence interval. So 95% confidence interval. That means the level is 0.95. That means our alpha, I just realized, alfalfa. Our alpha for alfalfa is 0.05. Cool. Okay, sweet. So let me get situated here. Let's do some math. So here's what we need, because we only have the data. We have the raw data here. We need to find the mean. We need to find the sample standard deviation, and then all the stuff for our hypothesis test. And here's what we know. Okay, so I have the overall conclusions kind of written out here, but I do not have the process. So let me just make sure I've got everything. Looks like I do. So let's first calculate x bar, right? That's going to be the not the hardest to figure out, and we'll recall, kind of write out the steps here. Sum of the xi's, right? Some of these things divided by the number that we have. Okay, so this is going to be 1.5 plus 1.8 plus 1.1 plus 1.9 plus, boy. And we'll divide all of this by how many things do we have? Well, we've got 1, 2, 3, 4, 5, 6. Sweet. Okay. And it turns out that is 1.6. Okay, and let me 1.6 tons. 1.6 tons. So let's write that over here. 1.6 tons. Okay. Now already we can kind of get an idea of what's going on here. Last year the average was 1.5, right? Now 0.1 ton, that's quite a bit, right? We're working with a pretty big scale here. But on the average here, not that much of an increase. And we'll get a better idea of what's going on when we calculate the sample standard deviation. Okay, so let's figure that one out too. Might as well, right? Well, we have to. So S equals okay. I'll write out the formula again. Xi minus the mean, we got that, squared, divided by n minus 1 underneath the square root sign. Very cool. Very cool. So what does that what does that look like? Okay, in fact, I'm going to write it down here so I have enough room. Okay, so xi, right, 1.4 minus the mean, 1.6 squared, plus, do it again, 1.8, whoops, minus, it is minus, right? Yeah, just double checking. 1.6 squared plus 1.1 minus 1.6 squared. Boy, I'm going to run out of room here. 1.9 minus 1.6. I'm going to have to really squish it. Damn. Okay. 2.2 minus 1.6 squared. Good Lord. Plus, what's the last one? Oh, yeah. 1.2 minus 1.6 squared. All right. This whole thing is divided by n minus 1. I hate that. So much. Okay, so when you work out the math, which, you know, oh wait, square root of this, sorry. Okay, so when you work out the math in this gross looking thing, turns out to be what the heck? 0.434. So just leave it at 0.43. That's fine. Tons. Very cool. Very cool. Okay, so what else do we need? Well, we found the mean, we found standard deviation of the sample, right? The sample mean, sample standard deviation. Now we can actually go on and find that t-stat. Okay, so we'll come in here, do it in a different color, right? Kind of color code things. Our what the heck? Our t-stat. Okay, that equals our sample mean minus the null kind of population mean, our given value, divided by the standard error, right? Which is just S divided by square root of n. Very cool. Very cool. Okay, so our mean is 1.6. Sorry if I'm giving you like vertigo here with all the sliding back and forth. Okay, so our sample mean is 1.6, and then our null, or our mu naught, is 1.5, right? That's what we're testing against. Divided by 0.43, 0.43 divided by square root of n, which is 6. Okay, square root of 6. All right. Very cool. Now it turns out that this equals, once you do all the math, right, 0.56. Okay, so that's our t-stat. So our t-stat here, highlight it, is 0.56. Cool. Okay, so we have our test statistic. Do we have our sample size? Yeah. Okay, so our sample size, our n, let me do it in this color. Our n, is 6. That means our degrees of freedom is 6 minus 1, which is 5. Now we have everything. We have everything that we need to throw into the t-tool. All right? Okay. So let me get that pulled up here. Zoom in. This is what it looks like, right? You should have the link too. This time, for sure. Okay, so the first thing you add in is our degrees of freedom. which is, and I have already forgotten because I'm a dummy, it is 5, right? 5. Now, I'm actually kind of curious. What if you put in 6 minus 1? Oh, yeah, it works. Don't do that. Don't do that. Just put in the actual value. Cool. And then, so that's 5. What was our t-stat? 0.56, right? Very cool. 0.56. Dope. Dope. Cool. Okay. So now, our p-value is 0.59. 0.59. That's huge, right? That is huge. Okay. So we'll just come back here. So let me actually label this. So this is, let me recall here. This is step 2 in that process. This is step 3. Cool. Step 4, find the p-value. Well, our p-value will go back. So based on our test statistic of 0.56 with 5 degrees of freedom, we're doing that two-tailed, right? Doing that two-tailed because we don't care about the direction. We're just wanting to know whether or not it's different. Our p-value is 0.59. Oops, 0.59. What was it, like 0.599, whatever? Yeah, we're gonna round that up. Round this mother up to 6. It doesn't really matter though. Our p-value is way greater than 0.05, right? Big time greater. Big time. Okay, so step 5. Step 5. We make our sort of conclusion-ish sort of thing, right? Conclusion. Where do we reject or fail to reject the null hypothesis? All right. Well, since our p-value equals 0.6, our alpha is 0.05, right? P is greater than alpha. So we'll say since, let me write it like this. Since P is greater than alpha, we do not have significant evidence that the true population mean is different than 1.5 tons, right? Okay, so we fail to reject. Let me write it in a different color. So it stands out, fail to reject H naught, right? 0.6 is way bigger than 0.05, right? Way bigger. Cool. Okay, all right. So we ain't done. We ain't done. Because even though we don't have evidence against the null hypothesis, we still want to find that confidence interval. And there's actually something interesting that's going to happen. Interesting that you'll see. Okay, so let's do that. Let's do that. So our 95% confidence interval. Okay, what do we need? Well, our formula looks like this, where it's, well, mu, right? Or x bar. In fact, I'll just write x bar here, right? Write x bar here just so you know what to plug in. We really know that it's mu. We really know that it's mu, right? So just kind of do this because that's the value you're going to plug in. Plus and minus our t critical times our standard error. Okay, and here's what we need to do. And actually, I do not have this worked out. So let me get my calculator out. Very cool. Very cool. So we know that our sample mean was, what, 15.2? 15? What the heck am I saying? It's 1.6. I'm a dummy. Okay, this is 1.6 tons. Let's do that standard error. So it was 0.43. I think that's what I said. Yeah. Divided by square root of 6. Okay, so 0.43 divided by square root of 6. So that equals 0.1755. Okay, so we'll just actually call this 1.8. Oh, great. My landlord mowing the lawn. Thanks, Brad. Okay, hopefully that's not too annoying. Actually, here, give me a second. I'm gonna shut the window. Give me a second. Does that help? Probably not. God, that is so friggin' annoying. That's okay. That's okay. Thankful for him. Okay. All right. So our standard error is 0.18, sample mean of 1.6. Okay. So all we need to find is this t critical. Okay. And let me write out up here just so we got it. Our degrees of freedom equals 5, and our alpha is 0.05. All right. A lot of fives. But that's all right. So let me go back here. Let me clear this out. Great. Sweet. Okay, cool. So what do I want to do first? Well, the first thing I want to do is plug in our degrees of freedom, right? And then all I need to do is plug in alpha over here, right? So this tool works both ways, which is really nice. And it turns out, check it out, our critical value, our t crit, is 2.57. We'll leave it at 2.57. And it's easy as that. It is as easy as that, right? So our t crit, 2.57. That's what I said, right? Yeah. Cool. So again, we only need the degrees of freedom and the alpha when we're finding our t crit. And it's the opposite for finding our t stat, right? Put in degrees of freedom first and then put in the t statistic, and that gets your p-value, right? So sort of this inverse sort of process there. Okay, so we have everything that we need. We have this. Whoa, wrong thing. We have this. We got this. We got this. Okay, so now all we need to do, a little bit of algebra. Not even algebra. A little bit of arithmetic. Okay, so it's going to be 1.6. And then actually, let's do it like this. Let's do it like this. Put it on a whole new another page here. So our lower and our upper. Okay. And so that just turns out to be 1.6 minus 1.8. No, 0.18. And what is going on here? 2.57. Sweet. 0.8. God, no. 0.18. And then 2.57. Right? Yes. Cool. So that's 0.8. 0.18 times 2.57. Okay, so that's 4.6. Yeah, we'll just say 4.6. So 1 minus 4.46. Good Lord. Losing my mind. That is 1.14. Very cool. And then the upper, same formula, we're just adding, right? It's 2.06. Very cool. Okay, so our lower bound, 1.14, and then our upper bound is 2.06. Sweet. So we are 95% confident that the true population mean is between 1.14 tons and 2.06 tons. Very cool, right? Very cool. Now let's take this, right? So actually before we do that, we're 95% confident that the true population mean, right? So the mean of the whole farm in this case is between 1.14 and 2.06 based on our sample, right? Now the thing here is that if we had a more sample, right, a higher sample size, a larger sample size, then this interval would get narrower, right? And maybe our p-value would be less than 0.05. Maybe. It was pretty large, right? But let's take this for a second. Copy. Come on over here. Very cool. So this is our 95 confidence interval, right? Very cool. What was our population? What was that null value? It was 1.5, right? It was 1.5. Well, where does 1.5 fall in this range? Does it fall in the confidence interval? This null value? Yes, it does, right? Almost in the middle, right? Almost in the middle. It doesn't matter where it is, but it's close to the middle. 1.5 tons, right? So it turns out, here's a fun rule, and we'll see this in a little bit too when we get into differences between two samples. But it turns out that if 95%, or not even 95%, we'll just say confidence interval. If confidence interval contains mu naught, this is always a rule. If the confidence interval contains mu naught, then P is always going to be greater than alpha, right? It's always going to be greater. So in this instance, it was helpful to find the 95% confidence interval based on our sample, right? Based on our sample. The sample mean, right? It was helpful in this case. Even though our conclusion was not, it didn't say anything about anything changing, right? It's probably going to be right around the same, right? It's going to be somewhere in here, right? Somewhere in here. But, right, so that's helpful for the farmer. But in our case, from a statistician kind of point of view, we know that if the null value, if the thing we're testing against shows up in our confidence interval, then the p-value is always going to be statistically insignificant, right? So we can even go back to our conclusion here, our hypothesis test conclusion. And let's see, how could we say that? We could say since the p is greater than alpha, right, we don't have significant evidence that the true population is statistically different than 1.15. Gosh, 1.5. Sorry, I keep doing that. We do not have evidence that the difference between our sample and the true population is statistically different, right? That's another way you could kind of say that. But the general rule of thumb here is what I've got written, right? If the confidence interval contains mu naught, then P is always going to be greater than alpha, right? Or the thing that you're testing is going to be statistically insignificant. Now, for the farmer, this might have been like practically significant, but for us, we don't care anymore, right? P is greater than A, our 95% confidence interval contains the thing we're testing against, right? Therefore, that's that, right? Okay, so that's the whole process here. And honestly, the thing that takes the longest, is finding the mean and the sample standard deviation, right? Once you get the t-stat, chuck it on into the t-tool here, and you're set, right? And then the confidence interval, you just kind of have to do an opposite process, right? Always use the two-tailed option, and you'll be set. All right, we'll move on to a different type of t-test here in a second. So I'll see you there in just a little bit.